Thank you all for joining us for this panel at the Informing Gravity Theory Through Quantum Simulation Experiment workshop. And the title of the workshop is also intended to be the theme of the panel. I will be moderating this panel together with actually Xiaoliang. She has volunteered to jump in because Brian Swingle couldn't make it in the snowstorm. So Xiaoliang and I will moderate. We're very fortunate to have with us on the panel Douglas Stanford, who's professor in the physics department here at Stanford. Steve Shenker, who is the Richard Herschel Weiland Professor of Physics here at Stanford. Manuel Endres, who's an experimentalist, hopefully many of you heard his talk. Manuel is Professor of Physics at Caltech. We have Lenny Susskind, who is the Felix Bloch Professor of Physics here at Stanford. And Dan Carney, who is a senior scientist at Lawrence Berkeley Lab. And more or less, Manuel is the only, tried and true experimentalist on the panel, but I gather that Dan Carney is also starting to move in the direction of experiments. And so that's who we have with us today. And I thought I would just kick it off by starting with a question primarily for the theorists, which is what question or questions in quantum gravity would most benefit from experimental input, and also what types of experiments are relevant. So that could range from precision measurements of gravity in our universe to perhaps more the topic of our workshop, quantum simulation experiments, or even sort of direct probes of strongly correlated materials. So I will pass it on to the panel to say what questions they're interested in and what approaches might be fruitful.
I have some things to say. They're not necessarily your questions. On my iPad. Would you like me to do that?
Yeah, sure.
Okay. Yeah. For science in my head. Why am I half naked? I just came from the Y. I thought this thing was taking place at 2:15. Okay, look. I know what you would like me to do. You would like me to tell you what experiment you can do now within the next 15 minutes. I'm not going to do that. I'm not going to do that at all. I'll do something very different. When I was a very young physicist, I worked together with Yakir Aharonov, whose name you probably know, a very famous physicist. And we worked on various kinds of Gedanken experiments, how to measure 2π rotations, all kinds of interesting things. And we considered them thought experiments. We considered them, nobody's ever going to do these experiments. But they illustrated some principles. Well, people did the experiments. It took 50 years, 40 years. Some of the experiments were done much faster than that. So what I intend to do is tell you about Gedanken experiments, thought experiments that your descendants may do 50 years from now, maybe, with luck. That's my purpose. Maybe entertain you a little bit, maybe not entertain you a little bit. Let's see. What's so funny? What's so funny?
I'd like to see.
No cable connected. Somebody has to do this. I don't know how to do it.
Yeah, we'll get it.
Henry, can you do this? I thought you weren't going to be here.
Sharing call. There it is. Yeah. Okay.
Good. Okay. Let's.
Yeah, we see it.
Yeah, I know. Come on. What's going on? Where do I actually begin?
No one fly, right?
I'm trying to remember what I was going to say. Okay, here is the experiments that I think might be interesting. There's a special class of experiments which, from a black hole point of view, would be extracting information out of a black hole. In particular, extracting information from a pair of entangled black holes. An Einstein-Rosen bridge, exploring an Einstein-Rosen bridge. Many of you think that's impossible because of a horizon, but it's not impossible. So I'll tell you very quickly how you do it. You know about quantum teleportation. Quantum teleportation is a protocol for sending information through a entangled pair. That entangled pair doesn't have to be a pair of qubits. It could be a monstrously entangled pair of black holes or anything. If you have enough entanglement, you can do quantum teleportation. Okay, now there's two sides to quantum teleportation. The first is sending information through. The other is exploring the interior of the Einstein-Rosen bridge. How do you do that? Well, you do exactly the same thing that you would do if you were sending information through, except for one thing. You don't know with great precision what the state of the entangled system is. And that's your job. Your job is not so much to send information through, but to use the quantum teleportation protocol exactly as if you did know what the state was. But in this case, what comes out is telling you more about the state of the entangled system than it is sending information through. You're not concerned with sending information through. You're concerned about what is going on in the entangled system. So, for example, instead of having the entangled system in some particular entangled state, you don't know exactly what the entangled state is, but you use the same protocol that you would use for quantum teleportation. And instead of sending information through, you see what comes out, and you ask the fellow who comes out, what did you see inside? You will get some information about what was in the interior of the, if you like, of the Einstein-Rosen bridge, or if you like, the entangled. I could do a little bit of theory here. I'm not going to do it. I'm just going to tell you right now that there is this other side of quantum teleportation, which is not sending information through, but finding out or exploring the interior of the Einstein-Rosen bridge. With that protocol, it is possible to find out what is going on inside the interior of the Einstein-Rosen bridge, or in the interior of a black hole, or the interior of a massively entangled pair of quantum systems. So I'll just tell you that. It is not impossible to extract information from the interior of a black hole, or so forth. All right, so we want to talk a little bit about some really crazy experiments. I want you to imagine, I don't even know what it is. I want you to imagine in your laboratory that you have a silicon sphere. A big sphere with many, many degrees of freedom on it. By sphere, I mean the boundary of a sphere. A sphere, incidentally, mathematically, is not a ball. It's a surface. You have a surface made up out of silicon or whatever it is. You dope the silicon to make a system which mimics a certain kind of quantum field theory on the system. What kind of quantum field theory? A conformal quantum field theory with enough structure in it that it would qualify as a conformal field theory representing anti-de Sitter space. Now, what can you do with it? What can you do with it? You have the system, and the theorists tell you that this system contains within it a world, a whole world of gravity, perhaps a standard model, all sorts of things taking place in the interior of it. Can you communicate with the interior of it? Yes, you can. All you have to do is have a little hammer and tap the silicon sphere. That will send waves onto the silicon sphere, and according to our best understanding of ADS-CFT, there are degrees of freedom which mimic, I don't even know if the word is mimic, which really represent the interior, including possibly people or intelligences and so forth that can live in that. You can tap the exterior. From the point of view of the ADS-CFT idea, you're sending gravitational waves into the interior. Somebody at the center can read those gravitational waves, and in fact, can send messages back out. The laboratory outside the sphere can communicate with the CF, with the ADS, the anti-de Sitter degrees of freedom on the interior, and can the observers on the outside, technicians on the outside, can find out what's going on in there and what's going on in there. A world of gravity, a world of quantum field theory, a world of things that we might be really, really interested in, even though you might say it's a simulated world. I would say it's not a simulated world. Everything you do, every attempt that you make to find out if it's real in there will tell you that it's real. Every experiment that you try to do, every protocol that you try to do, communicate with the interior, the answer will be that you will get a message back saying, I'm real, and you better believe it. Okay, that's a kind of experiment which I hope in the future can be done. It can be done if we have sufficiently big systems, sufficiently big numbers of qubits and so forth, to teleport through an Einstein-Rosen bridge, not an Einstein-Rosen bridge, through a massively entangled system. We'll be able to explore it and find out what's going on in there, much as though it really were real. Okay, so that's the basic message. What is going on in there is gravity, quantum field theory, and possibly even intelligent creatures in there. Now you say, how is this different, for example, than having a big cube of matter, a cube now, not a surface, a cube of matter in which we simulate the standard model, for example. We have a whole bunch of lattice sites. We arrange those lattice sites so that they describe lattice QCD or maybe lattice standard model and so forth. How is it different? Inside that cube, we can engineer that cube so that the cube really is the standard model, and therefore it can contain everything that the standard model contains, including intelligences and so forth, and we can tap on it. We can tap on it and send messages into it. There's no reason why we can't get messages back out. So how is it different? How is it different than just having a cube simulating, a quantum cube simulating, let us say, the standard model? Well, here's something we can do. We can do a little exploration of it, and then decide to go into the cube, open it up, take a knife, slice it open, and see what's inside. We slice it open and see what's inside, and indeed we will find degrees of freedom on the inside, which represent all the things that we think could be in that cube. I say people, maybe electrons, protons, neutrons, whatever is supposed to be in there. We'll cut open the cube and we will find it. The ADS-CFT, the thing which I'm talking about, is very different. I'm only going to tell you one thing about it. It starts with a sphere, the surface of the sphere. We send messages into it and out of it. We explore it, pretty much the same way we might explore the cube. And then we open it up. We open it up to see what's in there. We find nothing. Absolutely nothing. That's the difference. It's a big difference. You open up the sphere and you find out that there were no degrees of freedom on the interior, inside the sphere. Everything actually took place on the surface of the sphere. The holographic principle. Again, the holographic principle is what's going on here. In that sense, it is very different conceptually than having a cube of matter which is simulating the standard model. Very different. You open it up, there's nothing there. That's all I'm going to tell you. Someday, I think these experiments, or some version of them, I think will be possible. It's not going to be tomorrow. It's going to be 20 years, 30 years from now. I don't know. Good. That's all I have to say.
Can I ask a question? Yeah, sorry. So my question would be, do you want me to go out and find a real black hole and do this?
No.
What do you want me to do?
I want you to build a silicon sphere and dope it up so that it.
Okay, we definitely know how to build those. We definitely know how to build silicon spheres.
Yep.
So you would like us to create a single atomic layer sphere.
Yeah, I don't know that it has to be a single atomic
Okay,
layer.
we'll go to 10. I don't know, something like that.
Something that will support a nice quantum field theory on the boundary.
Great. But on the other hand, like people have built such things. They've grown sort of for like defining the kilogram, such spheres. But they're not hollow, but okay, let's pretend like we can get rid of the silicon atoms on the inside. But on the other hand, that thing sits in a classical world, buffeted by.
It's a quantum world.
So you would like me to put my silicon sphere in vacuum, and you would like me to put my silicon sphere in vacuum,
Best put it
and
in
maybe it better be at zero temperature environment so that like I'm not interacting via black body. Great, and then I tap on it. And are you telling me that somehow, just good old silicon atoms, I will get messages from the inside?
Well, you first have to prepare it so that you know there's somebody in the inside.
Ooh, can you tell me how I do that as an experimentalist? Like I'm taking this very seriously. I'm just really sort of poking at how do I translate it into something I do?
Important that there's somebody. I take it back.
Yeah, sure.
You don't have to have somebody in the inside. You just send a message in. The message might rattle around a little bit and come back out as a signal getting to the boundary.
Okay.
You can explore that signal. You can ask, is that signal composed of what is effectively spin 2 waves, gravitational waves and so forth?
Yeah.
You can do LIGO experiments in it. You can measure the properties of the things which go through. You tap it at one end. You measure it at another end, and you ask what kind of degrees of freedom would give me a signal of the type I'm getting.
So maybe where I'm going at this is because I like this idea of Gedanken experiments. This is great. Because sometimes I get at the core of like what you really care about. Well, it gets at the core of what you really care about when you do these kinds of thought experiments. So I guess my question is, is the idea that yes, on paper, you can sort of write all these things down, talk about a conformal field theory, but what we actually have is access to things like, maybe one day, sort of arbitrary quantum computers and things like this. Does that count as your thought experiment?
Say it again?
Will that count as your thought experiment?
On a quantum computer?
Yeah.
Absolutely.
Okay.
Yes, absolutely.
Okay.
And that's probably the way to do it, is to build not a genuine silicon sphere, but a quantum computer whose logic is the same as a silicon sphere. Absolutely.
Okay, and you're saying it would be great if quantum computers could build a simulation that would correspond to what you just described, and if that could happen, you would sort of get all warm inside and say, "Yep, that's exactly what I wanted."
Right.
Perfect. Thank you.
So happy.
Yeah. Sorry, just want to rephrase a little bit what Lenny said to see if you guys agree. I also want to hear comments from other theorists. So I think I just want to clarify one point. I think the silicon sphere Lenny is talking about is some strongly correlated matter that if we realize that, we realize this kind of state which seems to have an interior but actually doesn't. It doesn't mean like any matter do that, right? It means some particular kind.
We'll say, yes, I have an interior.
Yeah, it's like it is doing much better than our like graphene sheets in the sense of pretending there is an interior. Maybe
I'll ask one more follow-up to that. So some of us heard before lunch from Manuel, who is building a quantum computer. He has, I guess, thousands of atoms quite well controlled in an array, and well, maybe Manuel can tell us more about what capabilities he envisions in the next couple of years, but I would also like to know what should he measure on it. Maybe Manuel, can you say a little bit about what you think the capabilities will be in the next few years with these atom array quantum computers, and then we can ask the theorists, what they would like to see measured?
I tried to follow along with what Lenny wanted to do, but I guess you want to do some ADS CFT experiment where I poke around on the boundary. That's basically what it is. It might not be 20 years away. It's just a question of size and what system. Is it 2D or 3D? Do you need it to be 3D?
No, I don't think so. I think-
Would be okay to have a 1D exterior. Yeah, okay. I think that's
Zero
But
plus
keep
one-
in mind-
0D would be good.
Yeah, even zero. Even zero.
Means all interactions.
What do you call it, 0D or 1D?
I think
You're talking about
zero
matrix
D,
theory or something like
zero
that?
plus one time.
Yeah, one time.
And 0D all to all, yes?
Yes,
Yeah.
that is enough. That is enough.
yeah. All is more difficult, but yeah. But there's all these
But-
like these kind of happy codes or something like this. Is this enough for your?
The one thing that's important is the number of degrees of freedom per lattice site has to be large.
Oh, okay.
That would be what is, it's called the central charge of the boundary field theory.
Uh-huh.
It needs to be a fairly large number.
How large?
And that may be what the primary difficulty in carrying out such things is.
How large?
The larger, the better. 1,000.
2? 1,000?
10 to the 12 or 10?
10 to the 12 would be great.
I cannot do 10 to the 12.
Shaking his head.
I cannot do 10 to the 12. Sorry. Maybe, I don't know, but
Don't ask what you can do now. Ask what your descendants may be able to do.
yeah, no, I would love for my baby to do it, but
Actually,
I can do it beforehand. I would.
I want to
also
make
do that.
a comment about the number that you need, which is that we know how to predict what will happen if the number of degrees of freedom is very large. In some sense, like that would be gratifying to see experimentally confirmed and so on. But maybe the more theoretically interesting scenario would be to try to understand what happens when n is actually not that large. Now, the problem with that is that, yeah, so that sounds like a win-win because it's easier to implement in a quantum computer with fewer degrees of freedom, and also maybe we would learn more because we can't do the calculations already.
Yeah.
The challenge, though, is that it might be hard to interpret. So if you have some small n data, we might not know how to interpret it to try to learn something about the bulk theory, about quantum gravity, truly quantum gravity. So the naive thing, like if quantum computational resources were unconstrained, the thing that you would like to do is start with very large value of n, compared to the calculations that you know how to do about like, scattering. So Lenny was tapping on the silicon sphere that creates some particles that go into the interior, and they will scatter with each other, and they'll scatter with each other weakly if n is large, and we can do the calculations and predict what should happen and find the final state and verify that. In principle, you want to do that for very large n, where you can calculate everything, and then sort of gradually decrease n and see what is happening. It might be that the stuff you learn the most by actually studying small values of n at the end, but it might be hard to jump there immediately.
Douglas's point is that the smaller n is, the more quantum the system is. So if you really want to be exploring quantum gravity, in some sense, you're interested in small n.
Yeah.
Mhm.
I'm wondering whether it's possible let's say we start with small n. Is it possible if you had the data that right now you can't generate numerically except in very small systems, right? So I guess I'm wondering, sorry, is it possible that quantum computers will push us to a regime where you have the data then for a regime that you can't calculate things classically, and you build some intuition, or, right, you don't know right now what you'll predict, but if theorists got to play with the data or think about creatively about how to analyze it, maybe you would find something in the regime where we can't currently calculate things. Is that true, or? Not sure. Was the question clear? That's the hope, right? Yeah.
You'll be learning something about systems that you don't know how to directly.
Right.
Yep. I mean, along these lines, I think it's important to stress, and well, I guess I should preface this. There's this science fiction writer, Arthur C. Clarke, who I think he wrote the book behind 2001: A Space Odyssey. He had some laws many of these science fiction writers have laws. And one of his laws is if you listen to an elderly but distinguished scientist and they say that something is possible, they're almost always right. But if they say that something is impossible, they're almost always wrong. So I'll let you apply that. But one of the most vexing things is if we are at finite values of the central charge, so the physics in quantum gravity is quantum, it's not that it's hard to calculate. It's not a question of not having adequate computers or graduate students, we don't even know the rules. Okay, we think we know the rules describing these quantum field theories. They're
The boundary quantum.
the boundary quantum field theory. It's incredibly hard to calculate. The tools of quantum simulation and maybe quantum computation will be an aid there. But in order for us to teach us about the other side of this duality, we don't even know the rules. We don't. If you gave us perfect data, we wouldn't be able to check it for some of these subtle questions. And they're not that subtle. I mean, one of the most basic things about quantum systems, bound quantum systems, is they're quantized. Their energy levels are discrete. Okay, the energy levels of the surface of the silicon ball are discrete. They're very densely spaced because the system has large entropy. The quantum computers that are under construction could give us the numerical values of those energy levels. We saw some of them for this icing system. Well, we want the analog for some much fancier system, but still they would be discrete levels. There would be numbers. We don't even know the rules to compute those levels using quantum gravity. We don't know what equations to solve.
All
We
right.
don't know the right variables.
I think Steve is being modest. He is one of the people who has been involved in putting those rules together.
But, okay, so you have to accept my statement that we don't know them. And it's not like some super complicated question. Just knowing those discrete energy levels. We just don't know what compute, we don't know how to program a computer, classical or quantum, to give us those numbers in this other language. We're in the process of translating between two languages, but one of the languages we don't know completely. So the process of discovering new things about quantum gravity is not just being able to calculate things you can match with some known set of rules. It's somehow sort of inspiring us to guess new rules, to guess the right formulation of rules, and it's very hard to predict what clue is going to help us with that.
So in other words, you're saying we are way behind the experimentalists.
Yes. Well,
It's complicated.
yeah, yes, I think that's a fair statement. Okay. We have a question from the audience.
Just wanna question for you that you are the experts in quantum gravity. Something that we can do very well in controllable systems is to measure things very precisely. So sometimes it's super hard to create complicated entangled systems, but we know how to measure. So the question that I always ask and want to know is that imagine that we can have an atomic clock or an interferometer that can measure at gravity at the very small energy scales. I mean, we are millimeters, micrometers, even smaller. So is there anything that we could measure at these very tiny energy scales that can tell us something about quantum gravity? Because I think this is where we can provide some answer, but I don't know what would be the good things to measure or.
I have a microphone. We're not talking.
I mean, you can ask very elementary questions, like, do we even understand the theory of quantum gravity at very low energies? And like, a millimeter scale is huge in terms of ultraviolet quantum gravity, so you can ask far infrared questions. Like, I'm sure you've heard of these ideas, like, can you do an experiment to make sure that gravity can entangle objects, things of that nature? So there are simple things. I think things like Lenny's talking about probing the inside of a horizon are more UV. You need sort of much more sensitive instruments to directly detect something like that.
There is another interesting element here that I think,
The Mac,
yeah, another interesting element here that certainly my colleagues here have been very, very involved in explaining to the world. Ordinary classical or semi-classical gravity, the kind that we used to thinking about, is a coarse-grained theory. It's like hydrodynamics, where the really fundamental degrees of freedom are atoms and molecules. How do we get to the hydrodynamics? We average. We average over ensembles. We may not even quite know what we're averaging over. We do statistical mechanics and so forth. It's widely thought, largely due to the work that took place from my colleagues here, that classical gravity or semi-classical gravity is an ensemble average, an average over, and exactly what it's an average over is not clear. It could be an average over time, little time separations. It could be an average over the coupling constants. But from the work that's been going on the last 10 years, is it 10 years? Something like that. It's become more or less clear that the gravitational side of things is not infinitely precise. It's more like hydrodynamics than it is like a terribly fundamental exact theory. The fundamental exact theory is probably more like the theory of atoms and molecules in the fluid. And we have yet to completely uncover what those microscopic degrees of freedom are. And maybe it doesn't even matter what they are. Many different setups are likely to lead to hydrodynamics on the one hand, but many different setups seem capable of leading to the same rough kind of semi-classical gravity. So that's another aspect of it that you need to be aware of.
I think Anna's question, if I understand correctly, is related to a general direction that I hope we can discuss more here, which is how to connect these two things. One is the simulated universe in the lab. The other is the actual universe with the actual gravity. And then is it possible to, like, all these simulated experiments can teach us something about the real world gravity, or the other way around, the very accurate measurements can teach about the simulated experiment? Yeah, I just want to
say one thing. When I said people here have done this work on ensemble averages, it wasn't me. It was my colleagues over here. So I want to be clear about that.
I mean, the question. I think we don't necessarily have to have the microphone, but yeah, maybe.
Oh, yeah.
I thought you were asking your question, but this is a naive question, so I apologize if it's obvious, but in your silicon sphere, which is a model by a CFT, as I understand it, and if you ask
it's a metaphor which you probably want to run on a quantum computer.
Right, but if you ask people on the interior, are they going to tell you they live in an ADS space?
In a what?
In ADS space?
Yeah.
And then when you open the sphere, it's just magic.
Yeah.
So they experience ADS space.
Yes. But all the real activity is taking place on the surface. Waves propagating around. But yes, they will tell you exactly what you just said. Crazy.
I just want to ask a follow-up to the last couple of questions, and then I will hand it over to other questions. Lenny, when you said it's increasingly clear that this, semi-classical gravity is hydrodynamics and when is averaging over.
Not everybody will
yeah.
agree necessarily.
Well, that was part of my question. When you say this is increasingly clear, is this clear within the framework of ADS-CFT? Is it something that we think applies to gravity in our universe, or do people disagree about that?
That's an extremely important and good question. Our experience has been largely with a particular kind of system. We call it ADS. It's a world that has a boundary. The degrees of freedom live on the boundary. At the present time, we have very little experience beyond that. I've been working on trying to understand de Sitter space. I don't get much feedback from people who are a little bit afraid of it, but the answer to your question is it remains to be seen. Work in progress, whether it's broader than just But, I imagine my colleagues here would guess that it's broader than just ADS. I hope so.
Does anyone else want to speculate on that while we're on the topic?
I don't want to speculate on it, but I want to ask a follow-up question, which is, do you think it's conceivable, and this is for all of you guys, do you think it's conceivable that there is an observable, even in principle, signature of the disorder in the real universe?
Oh.
If I do a bunch of experiments, do I draw the couplings every time?
Very hard.
No, but they're the same every time.
Go ahead.
The same every time.
Sorry, what was the question?
Well, so if you get sort of semi-classical gravity by disorder, averaging over disorder, if I'm an observer in the universe and the universe works like that, what do I actually see in my experiment? So do I draw the couplings each time I do an experiment, or Douglas said, I think just now, that it actually be the same every time, and so then I'm seeing some disorder realization. So do I really get semi-classical gravity, or do I see a deviation from that because I'm only in one realization?
Well, the idea is that semi-classical gravity is itself related to some kind of ensemble of boundary theories.
Right, so if I'm not actually averaging over the ensemble, it sounds like I wouldn't actually get exact semi-classical gravity as my observations.
Well, you might get it with some other stuff that we don't understand very well.
So can I take that as a yes? It's conceivable that there would be a signature of this?
Isn't the key word self-averaging and not self-averaging? Some things do self-average, some things don't.
That's true. I don't know if it's too relevant to the question.
Well, self-averaging means that the ensemble average is a good representation of any one of the individual instances. Certain things self-average that way, other things don't self-average. So, for example, with Douglas and Steve were involved in something called, what's it called? The thing with bumps. That's a
Spectral form factor.
Spectral form factor. The spectral form factor, if you will look at it in detail, whatever it is, in detail for a particular instance, with like that. Okay, so it doesn't really self-average. On the other hand, if you were to average it over a little bit of time or something else, it would be a nice smooth curve. So certain averages self-average, and for those, the ensemble average is itself a good representation. But not everything is that way. So you're asking then, are there interesting things which don't self-average? I think you're asking.
Yeah.
Yeah. I think the answer is yes.
I worry a little bit that the discussion about ensembles and is sort of revealing a theoretical confusion in holography that is orthogonal to the stated purpose of this panel. And
Really?
Related,
Really?
you had okay, you had a,
I have a question about complexity growth and how that could affect. So, like, you're thinking about simulating ADS, CFT on whatever, a quantum computer, a silicon sphere, whatever it is. Obviously, any physical setup like that's going to have some noise. And as far as I understand, simple operators on the boundary correlate to very large, very complex operators in the bulk. Doesn't that mean that, like, unless you can reduce the noise on your setup to practically zero, you're not really going to be able to control the bulk at all? Like, it just seems to me like you're going to have kind of, because of scrambling, you're going to have like an exponential growth in whatever the noise.
So that's an outstandingly good question, and it's a little bit above my pay grade as a theorist. I don't know. Experimenters, the people who you would ask about noise relief and so forth, it's something I don't know. How cold, roughly speaking, how cold does it have to be before you could do this experiment?
It just seems like it would have to be like, already keeping a quantum computer cold enough to do anything is pretty hard.
Yeah.
If because of frat scrambling, it's.
I don't see any reason that it has to be colder than that. So.
Let me ask a question for the theorists. We take a microphone. So I mean, I don't know. What? Is it on? Yeah.
No? Oh.
So experimentally, I'm not an expert for ADS CFT, but like from what I understand, there are basically two routes. Like one is if you want to simulate something. Like, okay, you can measure something in a clock. The actual reality, it's a different story. I don't know much about it, but if you do a simulation experiment, a quantum simulation experiment, you could try an analog simulation experiment or digital version, some trotterized version or error correction codes or something like this. So now, on the analog side, I think there's a very low-hanging fruit that has ADS-CFT correspondence, which is, to my knowledge, a 2D, 2+1 ON relativistic field theory, which to my knowledge should have some ADS-CFT. Yeah. And that one is realized in optical lattices, for example, if you do a bosonic superfluid to Mott insulator transition, that's the O2 version of it. And in these Rydberg systems, if you do the XY model variant, you could do a 2D XY model. And you could park it at the quantum phase transition, and the emergent field theory should be that. So now I remember from talking to Subir, and I was a grad student already, and now again, that there's some, for the low end version, from the O2 version, there's some sort of guessed to a certain degree ADS-CFT correspondence, and from that correspondence, you could, for example, predict the shape of certain dynamical response functions, for example, current correlators or something like this. They should have, as a function of frequency, finite temperature versions, they should either have a dip or like a peak, for example. And I would tell you something about the nature of the ADS-CFT correspondence. So is this, in the context of what you are describing, an interesting experiment to do, to measure one of those dynamical response functions for these, say, O2 or O3, 2D relativistic field theory, or do you not care in the context of what you guys are working on? Super cares, but that doesn't mean everyone does care.
ON as opposed to a gauge theory.
It's 2D regular relativistic field theory.
Yes, but
not
not a gauge
not gauge theory. Yeah.
There are theories of gravity which are not the greatest theories of gravity, but they are based on things like ON.
Yeah. Yeah, you just have to kind of stand on your head to call it a theory of gravity, though. Yeah. It's maybe a little worse than the SYK model in that respect.
A little?
Can you elaborate on
In
that?
some ways, a lot worse. Yeah.
Can you elaborate on what makes a good theory of gravity versus
Well,
to stand on your head? Or yeah.
Yeah, it would be one. So it would be one where, for example, the scattering of particles at high energies is approximately described by the scattering of particles in gravity. In the theory that you're describing, the ON model, that's not true. It's far from a theory of gravity.
Would you say it's very non-local in the bulk?
Yeah, it's probably very non-local in the bulk. There's like non-local on the order of the ADS scale. And to some extent, the SYK model is also like that. It's not, I think in some ways it's better than the ON model. In many ways it's better than the ON model, but not as good as N equals 4 experiments.
So if you did that experiment and measured the shape of this response function, which is apparently like very hard numerically to predict. So what did I learn then? I learned something about like a gravity theory that no one cares about. So. Except for Zuber, maybe.
Yeah, you learned something about the correlation functions in this quantum Vasiliev theory. It's not, Let me try to describe in a little more detail the kind of experiment that, there's no pen. Is there a pen? Maybe this is clear. This looks good. Maybe this is clear already from what Lenny was saying, but like, this is adding some more detail to what Lenny was talking about. So there's this soup can picture of ADS-CFT, which was referenced yesterday. And so the boundary theory is something you simulate with the quantum computer. And you prepare the vacuum state, and then you act with some operators here and here at different locations in space. And in the bulk, that creates some particles that travel into the bulk. And by adjusting the type of operator that you put here and kind of tuning it carefully, you can adjust, you can
set things up so that you can control the energy, the center of mass energy when these things meet. And okay, so what you could imagine doing is starting from some theory with very large n, and doing this scattering problem. And then we know how to calculate what you should find. In particular, you should find some small deflection of these particles. They come out at some slightly different angle. And we would know how to calculate the statistics for that angle.
From gravity.
From doing gravity calculations. And so we would be able to tell you basically what the final state would look like. We prepare this initial state vacuum, act with these operators, and then in the boundary theory, you just do Hamiltonian evolution on your quantum computer, and we would be able to tell you what the final state will look like at this later time. Okay, now what you could do is you could either decrease the number of degrees of freedom slightly, or you could increase the energy, and you can access a regime where we cannot tell you what you will get. So we won't be able to predict what the final state will look like. And in between those two things, probably, you know, dialogue between the theorists and experimentalists, we'll be able to learn quite a lot about the quantum gravity effects that take place here at these high energies. I think, so that's one thing that I expect will happen at some point in the future.
The gravity calculation are done with a standard GR, or Einstein equations, and that's it?
Yeah, yes. Basically treating general relativity as a quantum field theory and then studying scattering in that quantum field theory. Okay, that's one class of problems, or the problems where basically we know the theory in the bulk, at least approximately, and there are some things we cannot calculate. Then I think there's another class of problems, so a different direction that you could go, which is to change the boundary theory. So not decrease n or increase the energy within like the n equals 4 super Young-Mills theory or whatever you started with, but just change the boundary theory in some way. And there are interesting questions there about like whether whether there are other theories of gravitational scattering that could exist that we don't know about. So one of the topics of research in high energy theory is people try to constrain using abstract principles the types of S matrices describing scattering that are mathematically possible. And there's some belief that the types of S matrices that you get in string theory are unique up to given some assumptions. And it would be interesting if it were possible to simulate quantum field theories that were not n equals 4 super Young-Mills, you change in some way, and see if you can learn about different kinds of gravitational theories that we don't know about. Now, I think both of these two directions, one is like learning things we don't know how to calculate in gravitational theories we sort of are familiar with. The other one is like learning about possibly different types of gravitational theories. Both of these require like probably enormous quantum computers. And in particular, to be able to start with this regime where I have this starting point with large n where we can agree on what's happening. Maybe as a short-term thing that one could try to do, okay, what is a short-term thing you could try to do that is like practice for this or getting in the direction of this problem? And I think one answer to that would be this traversable wormhole thing that Lenny had discussed. There was a sort of controversial paper about this a few years ago. But I think the overall idea of trying to set up the traversable wormhole experiment in quantum computers sounds very interesting. Another thing would be to try to come up with, well, yeah.
Actually, Doug, can you elaborate for anyone who's not familiar with it on what the experiment is? Just
okay, so that's a different. So that's a different geometry than this, although it's similar. That's one where you have two quantum systems. So the two quantum systems are denoted by the left and right lines here, and the emergent geometry is in between them. And you design a Hamiltonian that is like the Hamiltonian for the left system plus the Hamiltonian for the right system plus some kind of coupling times some coupling between them. And if you pick these Hamiltonians to describe holographic theories and pick the right coupling, then you can make it such that the ground state of that Hamiltonian looks like this space-time geometry. And in particular, it's possible to send a signal from the left system through the bulk to the right system. And from the perspective of quantum mechanics, that's sort of non-trivial. And from the perspective of gravity, it's just the propagation of this particle through that space. And it would be interesting to understand, well, I think of that as a type of a warm-up for this type of problem, for one thing. But for another thing, what Lenny was pointing out is that if you have some slightly crappy boundary theory here, like not a real wonderful holographic theory, then something like this might still happen, but there could be some stuff in the middle.
Yeah.
And you could learn a little bit about the stuff in the middle by studying these. I'm not sure. The information you learn may not be like very high quality information, but maybe you learn something qualitative.
Can I ask one follow-up to this, and then I will hand it back to others for questions? So I think the appeal of this type of experiment you described is that I do some simple local operation, and then initially that it might seem that the information appears to be lost, but actually it's recovered in the other system, right? Which is actually quite surprising from the quantum mechanical perspective. I think the assumption is often that the observables we have access to are local observables, but I'm wondering if one has enough data and access to high order correlations and maybe good methods of, I don't know, machine learning algorithms for looking for patterns in the data, whether one could have a more direct way of accessing some information about the bulk. So in other words, one gets, I guess, full statistics of the states of all the qubits, and you can, in principle, with enough data, access high order correlation functions. Is that something that could teach us something about the bulk? That's a vacuum.
I mean, sure it would. The thing about these local things is that they're, in some ways, a little bit cleaner because they don't depend on any, they don't depend on assumptions about the bulk. So the types of observables that I was discussing here are like you shoot some things in and then you collect them later. That's something that is somehow less conditional on your understanding of the bulk theory. On the other hand, if you understand the bulk theory and the correspondence with the boundary theory a little bit better, then you can set up experiments that more directly probe the bulk dynamics.
Okay, but I would need to know what I'm looking for.
Yeah, you need to know a little bit more about the dictionary in order to set those up.
And then maybe.
Yeah, I just feel like in general we have dived into a lot into the different like possible theoretical proposals. I just want to change a little bit to hear from our experimental colleagues, including Manuel and Monica and Dan, everyone else, about what are the things that like experimentally can be measured very well, but hasn't been studied much in theory. Like these are possibly things we should, like theorists should work more on. What Monica just said is an example of that. Right? Like there are things that you can measure which correspond to very complicated correlation functions, which you can be measured now. I'm just wondering if there are other examples like this, like the new experimental capability enables these, but hasn't been studied theoretically.
Yeah, I gave half of an answer already. So I think maybe what I was getting at is that like you could try analog simulations of these types of problems, but like my suspicion was correct that I suspect that most of those will be kind of too simple for what you guys wanted to. Analog simulation is like kind of what I was talking about. Like you basically have a bunch of qubits that interact in a natural fashion and just drive them. So there's nothing digital about it. And that's often pretty clean and we have a lot of results on it, but you're restricted in the types of models. So one example is to say...
Does analog just mean it has a continuous time?
like instead of quantum computer with gates?
Yeah, it might also not be, is not universal necessarily, right? I mean, you have some Hamiltonian basically that's given to you by nature one way or another. You could try to do Floquet engineering or whatever, but I suspect that most of these systems are too simple in the end to really learn what you guys want to learn. So then you have to go down a digital route and try to do it. And then in principle, the universal quantum computer and the systems that we build, in principle, you can have naturally what they have all-to-all two-body interactions, so two-qubit interactions, or maybe three, maybe you can do Toffoli gates. But it's something like this. It's a few-body interaction that's in principle all-to-all, and you have to schedule it the right way, and then maybe you can do mid-circuit measurements and feed forward. Maybe that helps you for creating the right initial states, and then you trotterize whatever evolution you have to have, and whatever Hamiltonian you have to have. So and then the question in the end is just the error rates that you need, and I suspect that's the crux of it, that like probably a non-error corrected quantum computer might not have the necessary error rates to see something interesting. And then we might have to do a very large detour. Then we might have to develop error-corrected systems at a very low error rate, and then it might be a 50-year endeavor. I don't know to do what you want to do. I think that the question for the theorists in the end is like, okay, let's say you have an actual quantum computer that has 2-qubit, 3-qubit interactions, maybe has all-to-all, and I can schedule it the right way. What are interesting problems that I should program? So what's the lowest hanging fruit that's interesting? And then for that lowest hanging fruit, what is the error rates that I need, and how do I prepare states efficiently and so on? I think there you would need actual work for people to come down from their theory thrones and get some students who want to do some dirty work like that. And I think there actually we need the work to make progress. Because I cannot do that, and I'm not sure, maybe you can, I'm not sure, but we need people who can do that and are willing to do that. Because otherwise this is all sky in the pie. I mean, I don't care. I don't know how to do this, a pie in the sky, whatever, sorry, I'm tired, the baby. So this is some sort of my perspective. So I think we need to figure out what are the lowest hanging fruits that you can actually program in that way, and then what you need in estimate at least of system size, error rates, and so forth. I think that's the real work. And then we can try to do it. But without that, I don't know what to do, to be honest.
I think one piece of fruit that should be low-hanging is to do this experiment that was supposedly done, what was it, Caltech, the quantum teleportation experiment, to do it properly.
What would that entail? I'm actually curious.
More than 7 qubits.
More than 7 qubits, a Hamiltonian which is not composed of a bunch of commuting pieces, and to actually follow the theoretical protocol that was described by the actual experiment that was done was a start. You try to do as well as you can, but it wasn't very compelling. It was not a very good experiment. To do that properly, that's a piece of low-hanging fruit to really exhibit that you can extract information from the interior of what is a simulated Einstein-Rosen bridge.
That's the kind of fruit, though, that would be, I mean, that would be gratifying and an interesting paper and so on, but it's not going to probably teach us something new about quantum gravity.
Well, you point that yourself. You can probably get into a domain of parameters where we don't really know how to do the theoretical computation, right? Where the experiment would give us some information.
But I think it's not likely that we'll be able to interpret the results in a way that teaches us something new. Like maybe with the benefit of hindsight, once we understand quantum gravity better, we'll be able to say, maybe, we could have learned something from that experiment. But
yes. No, I don't disagree with you. I just, but we do what we can do.
Maybe let me try to change gears a little bit and say that one of the things that might be fruitful in this interaction is to use sort of generic phenomena that come up in thinking about quantum gravity to suggest rather generic many-body phenomena that might continue to exist outside the range of these rather complicated and fine-tuned Hamiltonians. And one of the things that's come up, and this has to do especially in these all-to-all systems where you have, let's say, n, maybe 50 degrees of freedom, but coupled in this all-to-all way. There's two things about that. These all-to-all systems generically thermalize quickly. They're fast scramblers. The other thing is that this large n, this large number of qubits, means that even though the quantum mechanical system can be quite quantum, its h bar can be pretty big, there is another description, roughly speaking, this gravity description, that's almost classical. This doesn't mean the quantum system is classical. If the quantum system is a bunch of anharmonic oscillators, you don't solve the anharmonic oscillator classical Newton's equation. You have to do quantum mechanics. But there are new variables like Hubbard-Stratonovich fields that behave almost classically. Now, there's something about classical systems that has been well known for a long time, and that is that the lack of chaos, integrability, is rather stable. That if you take an integrable system, like non-interacting particles, which is not chaotic, and you perturb it generically, it stays non-chaotic. This is the KAM theorem. What this says is if this classical gravity-style system is almost classical, it might have regions of non-chaotic behavior. This would mean that the quantum system would have, even if the energies are in the region where the system typically thermalizes very quickly, where for some reason these degrees of freedom stay together and don't thermalize. This would be, I guess, a many-body scar. But it suggests that there's a rather generic mechanism for many-body scars in these large N systems, where you look for an integrable point in the classical theory. And these have been found. They're sometimes called oscillons. They're vibrating waves of either gravitation or scalar fields. And people studied the classical Einstein's equations and find out, even though there's a lot of energy in them, enough energy that typically you would make a black hole, that's thermalization, where these things just stay around and oscillate forever. This means in a quantum system, something completely crazy is going on. A lot of energy, a system that generically fast scrambles, and yet it just doesn't thermalize. And the thermalization times, depending on who you talk to, they either scale like 1 over the number of degrees of freedom to some power, or maybe even e to the minus the number of degrees of freedom. So you have a huge hierarchy of scales for no good reason, except if you think about gravity. Right, so that's something to look for if you can make one of these all-to-all systems. Hunt around and see if you can find many-body scars whose lifetime scales with the number of degrees of freedom. Okay, that's a kind of way that maybe we can use this correspondence that doesn't depend on, being able to get into these detailed quantum gravity theories. That's all that I wanted to say.
Thanks. So James raising his hand for a while. Do you still have something to say?
No, it was exactly related to this comment about 0 dimension plus time would be fine. And I was trying to figure out, how do I tap on the sphere with my hammer when I have a 0D system? What would that look like?
You just act with some operator. So it's a 0D system with many degrees of freedom, and you.
It turns out I've looked in my tool drawer. I've never seen an operator in my drawer. So let me see if I can sort of maybe phrase it a different way. Do you mean that I go in and I make a local perturbation on a specific qubit, and I say do a spin flip? Would that be an example of what you mean by an operator?
Roughly, yes.
And then
what would I have to modify about what I just said to go from roughly to exactly?
Well, the operators you want to act with are some gauge invariant operators. I'm not sure if they'll be encoded as single qubit in the quantum computer.
I think you might need a bunch of ancillas.
So sort of do a series of single qubit rotations on multiple qubits?
Yes.
Okay.
And then measure some other expectation value of some operators later.
Sure. Eventually, you have to measure something, right? In order to read out what happens. I'm just really poking at this idea of in this metaphor that we were using of somehow tapping on the system. It is a local perturbation or is it a global perturbation? That's what I'm trying to figure out because you told me it was 0D.
Well, so in 0D there's no distinction, but in higher D you can use local operators, and in 0D. I mean, a kind of analog of that is that you could act with fairly simple operators. So
if I did a sigma x, that would be
to the subtleties we just discussed. Yes.
Yeah. So in 0D, there is a difference between simple and complex operator. Simple is like multiply, only applying to several qubits.
Okay, so basically like some kind of many-body spin flip or something like this is what you would like to do?
Yeah.
Okay, got it.
But
Sorry. I just think that, I will say that I think it's really important that we try to close the gap between the language the experimentalists use and what seems obvious to the theorists. And so when I ask this question, it may seem trivial to you, but I think if we're really going to start connecting theory to experiment, we really have to give some concrete examples of like, what would be examples of what we mean by otherwise abstract terms? If we don't, that gap is going to remain there. And I don't think there's any good reason for it. We can close that gap. We can find common ground and make these things work.
we're related to this comment and to the question. We were discussing. So there was a paper by Juan Maldacena. I think it's called A Simple Quantum System That Describes a Black Hole, which was, I think, his attempt to sort of improve on this language problem and to address exactly the question of how many qubits that you need. And what? It was within it was probably 2 or 3 years old. He says that you should study a particular quantum mechanics system, the BFSS Hamiltonian, or D0 brane Hamiltonian is what it's called, but it's basically a bunch of anharmonic oscillators coupled to Majorana fermions. And he says that you need 7,000 qubits to describe 7,000 logical qubits to describe a black hole in the Einstein gravity regime. So in other words, to start somewhere where we know how to do calculations that will reproduce what you will find, and then we can both learn something. That's what he says. Oh, and he also mentioned that 7,000, he said, amusingly, this is a little bit less than you need to break RSA. So.
Yeah, but I suspect that an average non-string theory specialist were to read this paper, they would not be able to decipher it into experimental terms. So I think what's being addressed here is not what the realities of how many qubits you need, but how do we convey information back and forth between these two communities, and that is something that
It can happen. It just takes work.
Clearly very important, and we don't do.
Can I?
Follow-up questions.
Oh, can I actually go back to this question about new experimental things and what they're? I think something that I never hear about in this sort of merger of fields, but I hear about in one half of these fields, which is the quantum measurement people, is the idea of driven dissipative systems. So, everything is focused in this world on like, unitary gates and all this stuff, which of course is beautiful, but in the real world, there's also these systems where external drives and dissipation are just essential elements, and they can be quantum controlled. And I just want to throw it out there for maybe the theory-oriented people, is like that's a regime where it would be interesting if there was some example of a, say a CFT-ish system that you could realize.
Can you explain a little bit more?
So, for example, in these analog cavity experiments, right, it's often treated where there's a cavity loss, photons go in and out, and it's often modeled, and if you're thinking about quantum simulation as like just a loss, but of course you can actually read out those photons, and then it's a measurable bath. And so I don't know if there's many examples in holography where people have sort of explicit control over such things, like, oh, I have this CFT and there's a bath. I know there was some work on this in this world of violence, but I've never seen it connected to these kind of systems.
Maybe just as a small comment on that, we also in these cavity systems have some tunability of how much of that information leaks out. We can't tune it to 0, unfortunately, but I wonder whether that's an interesting knob, because you mentioned this story yesterday about stabilizing the length of a wormhole by measurement, and maybe it's a knob that isn't being thought about much in theory, but could be thought about more.
Yeah, I wanted to briefly come back to what Steve was saying about these scar-like objects. So you're talking about I do some all-to-all connected qubit or Majorana fermion model, and then even at very large temperature, there's some emergent quasi-classical degrees of freedom. Is that?
Yeah, I mean,
And
what
I-
people have studied is not at very high temperature, but at moderately high, enough temperature where there are other situations that rapidly thermalize. So, the Hilbert space sort of breaks apart. So if you go to very high temperature, it's harder and harder to find these things.
Or to predict, yeah, I see.
But I should say that I don't know of an example that's been found in a kind of SYK-ish type system. The calculations pointing to these things are in these rather elaborate things where they do calculations in classical general relativity. And they find classical solutions that have a lot of energy in them that just oscillate back and forth. And sometimes they're called oscillons.
Oscillons, okay, I should look for this.
And,
I mean, it reminds me a bit about the stuff I talked
Yes,
about
exactly.
this lattice gauge theory.
But
And
these things are, the things you were talking about are classical in your boundary, in your auxiliary quantum system almost. These things would not be a classic, they wouldn't come from something classical equations of motion in your auxiliary quantum system. They come from studying classical equations of motion in this other description.
I see. So they would be potentially hidden to me if I just programmed the thing on a quantum simulator.
You wouldn't be able to reach in and find them, but if you dialed initial conditions, you would find something that you thought should thermalize right away and doesn't.
I see. But I might not necessarily see the oscillations. I see.
Yeah, there's a question about state preparation and that I think is confusing.
Yeah.
These states are rather simple. And so you might think that they're not that hard to prepare.
Mm-hmm.
So there aren't very many of them, but they're...
Sometimes these things happen because of hidden symmetries that you didn't realize were there. For example, these things that I call sloshers, which they're conformal symmetry. You're not talking about
No,
those. You're
these
talking
are
about ones
these
where
are,
there's no really good reason for why they.
The best reason that it has is that there's a way of rewriting Einstein's equations in a certain subsector that maps onto one of these classical integrable systems, like the Fermi-Pasta-Ulam system. Okay, that's got hidden conservation laws, but no good reason. And the boundary theory, certainly, there's no good reason.
I just want to, as a moderator, just want to encourage people to raise other questions, especially from the young people, students, postdocs.
I want to come back to the program, which I think it really would be worthwhile thinking about minimal experiments, even if they don't appear to be possible next year, that tell you something really meaningful and where you could really learn something. And I think really thinking that through carefully. I understand the comment about the Caltech experiment to make it better, but I don't know exactly what it means. How many qubits? What do you actually need? So this kind of thing, to think this through, what is some sort of a recipe where I could think along as an experimentalist and see how do I get there.
Well,
I think that's really missing in that community.
The only person who knows the answer to these questions is stuck in a snowstorm.
Brian, or Norm or someone like this. I wanted to be able to translate that stuff.
Brian is online. Do you want him to comment on them?
Brian, tell us what to do, Brian.
That's it?
Just have a good attitude.
He's just laughing.
Here, I'll appear myself. What should you do? Well, yeah, I like these traversal wormhole things. I think, sparse all-to-all models are very achievable with these reconfigurable atom arrays, among other places. And yeah, I think the hardest part is preparing a low energy state, but maybe something adiabatic can work reasonably well. But yeah, we know like roughly how to make thermofield doubles now. We know how to couple these things in a gravitational way. So I think we could do this experiment with not, 100 logical qubits would be already quite interesting. They don't even need to be fermions. We can do it with spins. And Douglas earlier said that he didn't think we'd learn anything, but I'm not so sure. Like in the SYK language, if we like mix a little bit of two-body interaction in, would we really not? Do we know what's going to happen there exactly? And do we know what the gravitational interpretation of that is? Or like there must be some knob we can tune where we're going to learn something. I just don't. I can't imagine we know it that well that we wouldn't learn anything from the bulk point of view.
Also, some of these phenomena exist in high temperature. It doesn't have to be low temperature.
That's true, yeah.
So, yeah. So that's another good thing for experiments.
But I think we could definitely prepare like a moderately low temperature state of a sparse spin SYK type model and study the dynamic using, an analog simulator or some atom motion. And that would be interesting, I think. As an example.
So Brian, I have a question. There are some of us who are interested in an interesting limit. It's called the double scale limit. It's the limit in which each term in the Hamiltonian contains more and more spins, or whatever we call them. In particular, the thing we sometimes call Q or P grows with N. Is that something that we're going to be able to simulate or be able to do in? I'll explain more if somebody wants, but I think Brian knows what I'm talking about.
Yeah, I think so. In particular, we know that for fixed P or Q in your language, we can recover the physics.
P is the number of degrees, the number of qubits in each term in the Hamiltonian.
Yeah.
Yeah.
What's Q?
Sometimes Q, sometimes P. Yeah. Okay. Right.
Originally Q, and now P is more popular for various reasons.
Right. Okay. So one very interesting limit is the limit in which P or Q grows like the square root of N. Why? It's an interesting limit, and I'm just wondering if that's something that is feasible experimentally.
It is. I think it is.
You think it is?
Not the full model, but because there's too many parameters in the Hamiltonian.
Yeah.
For example, I used to give this analogy with 50 qubits and Q equals 8. There's like 200 billion terms in the Hamiltonian, which is a lot to ask your experimentalists to. That would be 200 billion frequencies that Monica needs to program into her.
Yeah,
might be a bit much. But in the paper that you're on with me, we show that you can get the same physics with 200 terms.
Yeah.
So yeah, I mean, I think it's conceivable. We need to think hard about the scaling and all that stuff, but it doesn't seem outlandish to me.
We put it in a proposal how to do that specific. I think I try to read the paper. But I think I know how to digitally simulate that model. I mean, there's some tricks with ancillas to get the right terms and whatnot. But what would be the right experiment to do the most interesting? I cannot thinking about doing it, but I would need to know what and if it's worth it versus doing error correction code, which is the other thing.
Me?
I don't know anyone. You or Brian? What is the most interesting thing to do first?
Simulating Visitor space.
Yeah, but what state should I prepare, for example? Let's say I can trottleize the Hamiltonian, and then what do you want me to do first?
Trottleize the Hamiltonian.
Yeah, I can digitally do the Hamiltonian. Let's say I can do it.
I barely know what that means. I know what it means, but I have no answer to your question.
Does Brian have an answer?
Yeah.
Well, I'm not as up on the de Sitter story, so I can't comment on that so much. But you could make thermofield double and do wormholes. So you just make the thermofield double, which I can tell you how to do, offline if you like, or anybody, Chi of Molosena and Chi is sitting 2 states down from you. He can tell you how to do it.
Yeah.
And yeah, then you could do the wormhole experiment. That would be super interesting.
Okay. Yeah. We can do bell pairs basically. Okay. Okay.
Just Just one.
Since we mentioned these wormholes, I feel like one question to experimentalists is what aspects of these physics is universal, right? It means like there are particular models that we know how to compute things, and then incrementally we can measure and compare. But then there is many other models with similar structure, like some chaotic system, two of them coupled, and then there may be some kind of teleportation that give you a similar wormhole, which we don't know how to compute theoretically. And if incrementally you study these kind of systems, maybe you'll find some empirically some universal phenomena that we just didn't know before. I think that's one example of things that are, this universality may be one aspect to look for incrementally.
I just wanted to make one quick comment, which is I love these questions about, what exactly would we measure, and it connects also to James's comment earlier that there is something of a language barrier between fields. And even if the first experiments are ones where we won't learn anything yet, I think if we start to overcome the language barrier, that's already important progress. With that, I want to follow up on Xiaoliang's request to have some question from a young person in the audience.
There were some hands.
Oh, yes, great.
So, as I understand it, it's generally expected that there are a small set of theories that have holographic duals, that this is not a generic property. But there seem to be some things that people look for to, start building up a dictionary and say this is likely to have a dual. Is there things that, like an experimental CFT, properties that it should have that experimentalists could know, like we want to look for this as like an indication that this system that we probably don't understand has a holographic dual?
I think the answer is two things: large N and strong coupling. Large N in the holographic side, very strong coupling, and large N. I think that pretty much.
Particle number or degrees of freedom per particle?
What's that?
N is particle number or degrees of freedom per particle?
The number of degrees of freedom. It's called the central charge.
Okay.
Yeah, that should be large. And the other thing is that the coupling constants need to be very large.
So
Mike,
what?
1. Actually, one is good enough. It shouldn't be in this Tuft limit where the coupling constant goes like 1 over n or something.
It's like the ratio of interaction energy with kinetic energy.
There we go.
Yeah. So, okay. I think those, as far as I know, those are the main 2 ingredients: strong coupling and large N.
But it's not. If we have these, we know it's holographic.
Right. But if I had to guess, I would guess that's more or less the basic ingredients.
But maybe there are 2 sides to the question. One is what ingredients should we put into the experiment? And then what types of observables, if we're not sure whether it's holographic, what should we be measuring?
What type of things should we look for? If this, first you should check that the system thermalizes.
Oh, good.
Okay. But the thermalization time should be of order the temperature or the inverse temperature with no small or large factors. Okay, no e to the 10th times the inverse temperature. Order 1 times inverse temperature. Okay, that's an empirical check.
Hole or for anything holographic?
Anything.
Well, I think I'm not sure what we mean by holographic. A system that's roughly described by gravity, its high temperature states will look kind of like black holes, and this is one thing a black hole does.
Yeah. So you add my list of chaos.
Well, yeah. Although I think it would be a way of measuring what you called strong coupling, is that this would be the case.
Strong coupling theories be integrable?
Well, I guess all right, maybe this is semantic. Okay. But that would be something to look for that's experimentally acceptable. Look for systems that thermalize as quick as you can.
But beyond SYK, are there models that are concretely showing that?
Yeah.
Beyond
Yes,
SYK.
Besides SYK?
Yes.
We don't know how to do the calculation in them directly, but we can write down Hamiltonian that we strongly believe has that property.
I think any coupled matrix system will do this. I think
We'll have what?
we'll have a thermalization time.
Beta? Or?
No, but of order beta.
Okay.
No, with no 1/n's or small parameters.
Yeah. Well, but that probably doesn't count as holographic. I mean, the question is tricky because what you mean by holographic is not clear. Like, I think probably by sufficiently generous definition, every quantum system has a holographic dual. It's just that the description in using the bulk theory is not useful, and it's useful and simple when n is large and lambda coupling is large. I think it's also probably not super useful even if the thermalization time is, order the thermal time as well, if the coefficient isn't right.
Could I just ask for
It depends
clarification?
for what purposes. Okay.
Could I ask for clarification between this and the earlier comment? Because, okay, in this comment, you're saying if you want to find a holographic system, modulo the issue that, it's not clear exactly what that means. You want to look for fast scramblers that thermalize very fast. But earlier you were saying Ham theorems gives you a motivation that, like, actually you want to look for scars and slow thermalization because this indicates there's some hidden, like, minimal classical description of the system. I guess in some sense what you mean by it has a good holographic description is that, like, there is a low complexity classical description of the large N version of the system or something like that.
Well, in those systems with these many body scars, with these oscillons, most states will rapidly thermalize. And then if you imagine perturbing those states, you will find this fast scrambling behavior. Okay, but these rather generic but special initial conditions will not thermalize, and they will not fast scramble. Okay. But so you would have both in the same theory, depending on how you prepare the system. I think there's a semantic question about if you want a system whose description is Einstein gravity without any other stuff, then you have to work much harder. There is a slightly larger universe of theories where you might have Einstein gravity plus some other stuff like strings. Okay, that doesn't take quite as strong a coupling. Okay, and I guess those systems might be easier to achieve. Okay, and then there are systems that don't fast scramble at all, and those would be even stranger. So there could be hierarchies.
Even within the black hole context, it can be states which don't obviously fast scramble. Just something orbiting the black hole.
Right. That's
something orbiting a black hole that can last for a long time and doesn't fast scramble. So it's a little bit complicated what you mean by
That's an example of it. That's another example of a many-body scar that you can.
Right, and translating that into the holographic terms, I'm not sure what it means exactly, but
in the boundary.
I know what it means gravitationally as well. Orbiting a black hole.
But let me ask a super stupid question. So let's say, ordinary gravity that we look at is very classical, right? There's gravitational waves and so on. Are you saying that in a sense, what eventually you need to have is a theory that has a gravity dual that both describes black holes, so there's fast scrambling, all of that, and I found the right classical degrees of freedom within the whole mess that describes my gravitational waves and my planets orbiting and stuff orbiting the black holes and so on. Is that the essence of it?
Yeah.
I see. In the end, I need both basically, and I need both in the right way. I see.
If you want a full-fledged.
Yeah. I'm trying to get it.
Special theories we found seem to have all of that.
I see. So these theories, they're not just have the fast scrambling, but I found some emergent degrees of freedom in a way that describe.
But I think it's believed that those things go together. Like it's not like you would have to do some separate search for fast scrambling and also for these many body scars.
That's interesting.
The many body scars, these long-lived states would be automatic if you have the very fast scrambling.
But is this true for, say, SYK or something like this?
SYK is sort of a special example because it doesn't have extra dimensions in the bulk. Yeah. But we have a higher dimensional bulk theory.
Oh. So this doesn't have to kind of, what are they called, oscillons?
I wonder whether you can complicate the theory a little bit by sort of, but I don't know, like if you add matter or something.
So what's the simplest theory that has both?
I don't know.
No one knows?
A simple example of what the difference that Lenny was talking about, these orbiting particles.
Yeah.
So in SYK, the bulk dual is like 1 plus 1 dimensions. You cannot orbit.
Yeah.
And there's a similar problem in 2 plus 1 dimensions in the bulk where you cannot orbit. But in 3 plus 1 dimensions in the bulk or higher, if you have a gravitational theory, then you can make this black hole, which is very rapidly thermalizing. But you can have, classically stable orbiting trajectories that live for a very long time.
So like a really cool experimental results would be if I did something that you could conceivably have a gravitational dual where I observe both of those things depending on the initial state. So one thing I see fast scrambling and it has the right scaling, and the other thing is I see some sort of scar thing at the same time. That would be exciting.
Yeah.
Okay. Brian, tell me what to do.
Okay, I wish we could keep going for another hour because I feel like we just got started in bridging the language barrier and now we're making good progress. But instead, I'm going to ask Lenny, since he had his hand up, to offer any final words of wisdom.
Physics question, the other question which has come up, how do we open and keep open the channels of communication that I'm not sure who you are, but whoever you are, I think you were right on the money with respect to this issue of keeping the communication channel open. I'm very interested in it. We had a number of years ago, before COVID, we had a set of conferences. What do we call it? Quantum Gravity in the Lab. We sort of started it out, and I think it would be a good thing to sort of institutionalize some way of keeping these channels open.
They're supposed to do one every year of this.
Well,
that's what the Heising Simons contest.
Yeah. Okay. So
you need more workshops like this.
Where? In Boulder. In Boulder. Okay. That's fine. Sure. Well, look, I'm 85 and a half years old. Who the hell knows what I'll do next year? Don't count on me, but
It would be nice if you can.
It would be nice, especially for me.
So,
with that,
thank you all for participating in the panel and everyone in the audience who chimed in. I really enjoyed this, and I hope we'll get to do it again. So.
Thank you.